Welcome to the Foundry by Forge College. Let's jump straight in. Today's explainer takes everything we covered last time about performance metrics and, well, we're putting it to the ultimate test. We're taking those abstract numbers and applying them to actual, physical, and logical deployment blueprints for Firedancer. Think of this as the exact moment where theoretical math finally meets the cold, hard metal of the server rack. So you've got the metrics. Now, where does Firedancer actually live? Because here's the reality of advanced validator architecture. Things like end-to-end latency and RPC amplification, they're literally useless if we don't know where we're installing the engine. You could build the most highly optimized execution engine in the world, but if you bolt it into the wrong chassis or wire it up inefficiently across your data center, you are not going to win the race. Where you physically place your processes dictates the absolute limits of the performance you can squeeze out, period. All right, here's our blueprint for this explainer. 1. Core deployment patterns. 2. The co-located single-host setup. 3. The separated worker model. 4. Edge and hybrid models. 5. Real-world operator scenarios. And finally, 6. The comparison table. Let's get to it. Section 1. Core deployment patterns. Let's map these logical components directly to our infrastructure. First up, the co-located single-host pattern. This is where your validator core, the RPC layer, and the Firedancer worker all run on the exact same physical or virtual host. To use a fun analogy, deploying this way is kind of like cramming your entire startup team into a tiny, one-room studio apartment. Communication is instantaneous, right? Because everyone is practically sitting on each other's laps. Passing notes takes zero time. But there's absolutely zero privacy, and if something goes wrong, say someone burns the toast, the whole apartment fills with smoke and nobody's getting any work done. Looking at the engineering reality of that studio apartment setup, you're heavily relying on local IPC, inter-process communication, and shared memory. This bypasses the traditional network stack entirely, which is a massive performance boon. It minimizes serialization overhead and gives you the absolute lowest median latency possible. Data doesn't need to be packaged up, sent over a wire, and unpackaged. It's just there. But remember that burnt toast? You suffer from incredibly tight coupling. You're in a shared fault domain. If a rogue process suddenly hogs all the CPU cycles, your entire consensus mechanism goes down with it. It requires massive single-host hardware capacity to pull off safely. Moving on to Section 2, the separated worker model. Trading latency for isolation. If the last model was a crowded studio, this one is like moving the Firedancer worker into the apartment next door, connected by a high-speed private cable. The crucial thing here is the conscious trade-off you're making. You're gaining phenomenal fault isolation. You can scale, upgrade, patch, or even outright restart the worker nodes without ever taking down the critical validator core. Your consensus just keeps ticking. But you do pay a tax for that peace of mind. That tax is network round trips, heavy serialization costs, and a noticeably higher 99th percentile latency baseline if your internal network hits even a microsecond hiccup. When we look at these two side by side, the trade-off becomes totally obvious. On the left, the flat, shared memory of colocation gives you raw, unadulterated speed, but a terrible blast radius. One thing breaks, everything breaks. On the right, the separated model gives you a sturdy safety net, isolating crashes, but it introduces network RPC and remote caching overhead. The big takeaway here, your physical placement directly dictates your software mechanism. You literally cannot cheat physics. Section 3, Edge and Hybrid Models. Balancing regional proximity with centralized execution. So, what if you want the best of both worlds? What if you scatter lightweight RPC frontends globally, so they're right next to your users, but you keep the heavy lifting Firedancer workers centralized in a massive data center? Well, that's the hybrid profile. It's absolutely brilliant for optimizing client proximity. If a user is in Tokyo, they hit a Tokyo-based frontend, and simple read requests are lightning fast. But for heavy write execution, that Tokyo frontend has to phone home to your central cluster halfway across the world. So you get great regional availability, but a massive risk of centralized bottlenecks. If you don't actively implement aggressive caching and sharding, those central workers are going to get totally crushed. Section 4, Real-World Operator Scenarios. Let's put these blueprints to the test. Here at Forge College, we love practical application over pure theory. So let's look at some real industry profiles. Meet Operator A, the exchange. They're running a single-region, high-end production validator. Their traffic is incredibly high volume, and they are ruthlessly latency sensitive. A difference of just a few milliseconds, that can equal millions of dollars in arbitrage. Because of this, the exchange strictly uses the co-located single-host model.
They demand the absolute lowest possible median latency, and they will gladly pay for top-tier hardware to get it.
However, there's a distinct danger zone here. Notice how during a normal steady state, their CPU usage is totally fine. They're cruising. But under peak load, like a massive market event, aggressive transaction execution can instantly saturate all available CPU threads. Because they're co-located, that CPU steal can literally starve the consensus process. This causes catastrophic latency spikes right when they need speed the most. To survive, they have to over-provision memory, buy the most expensive processors, and watch that CPU headroom like a hawk. Now let's consider Operator B, the RPC provider. They aren't doing high-frequency trades. They're serving infrastructure to dApps globally. Because their users are everywhere, they rely on the edge and hybrid model. They keep read-heavy operations right at the edge, ensuring simple queries like checking a wallet balance feel instantly responsive. But what happens when a complex, smart contract transaction rolls in? Step 1, the regional front end receives the heavy transaction. Step 2, it quickly realizes it can't execute locally, so it fetches the account state. Step 3, it bundles that data and offloads it across the network to the central Firedancer worker. This extra, mandatory network hop is exactly where severe RPC amplification happens. It generates way more internal traffic, and it's precisely why you see higher P95 and P99 latencies for write-heavy users in this scenario. Finally, meet Operator C, the cost-optimized staking operator. Their goals are completely different. They aren't trying to win a high-frequency trading race. They prioritize predictable, rock-solid 99.9% uptime over absolute maximum throughput. They want steady yield, and honestly, they just want to sleep through the night without frantic pager alerts. So they intelligently opt for the separated worker model. Because of this setup, they gladly accept a slightly higher median latency baseline every single day. Why? Because during a sudden traffic spike or a software bug, their fault domain is perfectly isolated. The worker might choke or restart, but the validator core remains totally untouched, just humming along in the next room. They can even use simple horizontal redundancy, like running duplicate, cheaper workers behind a basic health checking proxy to make sure consensus voting never skips a beat. Section 5. Building the comparison table. Let's look at the final artifact. So, we've explored the patterns and seen how real operators adapt them. Let's compile all of this into a concrete artifact you can actually use for architectural decisions. If you choose colocation, you can hit a blazing fast 5 to 10 millisecond median latency, but you're going to need something massive, like 32 vCPUs on a single box, just to be safe during spikes. If you go separated, your baseline latency jumps to 8 to 15 milliseconds, but your resilience skyrockets because you've isolated your faults. And if you go hybrid, well, your core metrics become entirely dependent on which physical region your end user is in relative to your central workers. If you take nothing else away from this explainer, remember these 3 core deployment principles for Firedancer. Principle 1. Physical placement completely determines your software mechanism. You can't optimize around physics. Principle 2. Separating workers adds a network latency cost, but it successfully buys you crucial sleep-saving fault isolation. And Principle 3. Edge patterns are fantastic for user proximity, but they strictly require proactive sharding and caching so your centralized layer doesn't become a fatal bottleneck. I'll leave you with this final provocative thought to test your own infrastructure assumptions. When you design a system, are your deployment choices actually backed by measured empirical estimates, or are you just relying on convenient anecdotal claims from other operators? In high-performance Web3 architecture, simply guessing just doesn't cut it. Thank you so much for joining me for this explainer. I highly encourage you to head over to forge.college to continue your Web3 learning journey and dive even deeper into advanced validator architecture. See you next time.